First of all, we'll see what is an event, right? An event is a change in the value of either register or net. If the register or value of a register or a wire or net is changing from one logic to other logic, that is called an event, right? Either it can be edge or it can be level, right? From changing from 0 to 1. So based on the type, we have four different types of events. One is regular event control, second one is named event control, and event or control, and third one is level sensitive. We'll see all the four in the coming slides. So what do we see? We have a event, and then based on the event, you can trigger to perform some statements, either a single statement or block of statements. You can perform based on the event. The event is used for triggering some set of statements, right? So let's begin with regular event control. We'll use a symbol called @ to trigger the set of statements. Okay, so this is an event control symbol. Remember, @ is used for event controlling. There can be either positive transaction or negative transaction of the event. So whenever there is a positive transaction, we can use a keyword called posage. Whenever there is a negative transaction you want to control, then you can use negage. You are not controlling, you are just using that event to trigger some other statements that needs to be executed. So this is positive edge and this is negative edge event. Okay, so let's take an example. I am writing @clock, my q is equals to d. So this is one event. It is checking for whether the clock is changing its value or not. If the clock is changing its value, then the d will be stored inside q. Similarly, @posage clock, my q is equals to d. What does this do? The d will be assigned to q only at the rate of positive edge of the clocks. We have clocks like this. At every positive edge, the d data will be assigned to q. Okay. So the positive edge can be two different ways. One way is the positive transaction from logic 0 to either 1, this is also a positive edge, or logic 0 to either x or z. Both of this is a positive transaction. Okay. Even if it is transaction from this x and z to 1, this is also a positive transaction. Okay. Whenever you write positive edge, it means whether it is transaction from 0 to xz or 0 to 1 or xz to 1. All these things are positive edges only. Similarly, you can write @negage, which is a negative edge of clock, q is equals to d. So what does this do? It will assign d to q when there is a negative edge of clock. So negative edge means like this. Similarly, same as positive edge, we have two different kinds of negative edges, like whether it is going from 1 to either 0, this is also negative edge, or it is going from 1 to x comma z, this is also negative edge, or it is going from x comma z to 0, this is also a negative edge. So in these three conditions, it will execute q is equals to d. And you can specify like this also, my q is equals to my posage of clock d. So what does this do? What is the difference between this and this? The same thing that we have seen in the earlier slide, right? First it will execute this expression, and then it will wait for this positive edge clock. Once the positive edge clock is arrived, then it will assign the data to q. Similarly, we have seen in event based triggering, this delay based triggering also the same thing, right? We have seen it will execute this first, and then it will execute for this amount of time period, and then it will put the data from right hand side to left hand side. So that is about regular event control. Now we'll see what is a named event control. In Verilog, we have a feature called you can name the event as well. So how to do that? You can declare the event by using a symbol called this dash and greater than symbol. So how to do that? We'll take an example. Let's say I want to name my event receiving of data. So once I have this event, if I confirm that whether the complete data is received, then I will perform some steps. So this is my event name. Earlier we have events of like positive edge of clock or negative edge of clock or at the rate clock. So these are not in our control. We are not naming the event, but here I am naming the event also. At what event I want to perform the following steps. So this is my naming of event. So next I am assigning always at the rate posage of clock. Inside this posage of clock, I want to assign my statements after happening this event. Okay, at the rate of posage of clock. Now begin if this is my some statement, like if my last data is arrived. If my last data is arrived, then this will be become one at this time period. So this is my event detection. So this symbol I am using dash and greater than whether the received data. This is my name of the event, right? REC data. This is data. If this happens, so when the last data arrives, then trigger this event and then end. So we'll use this triggered event using one more always block, always at the rate my event. This is my event, right? Receive data. Once this data receive data event is triggered, then it will go to this always block and then it will assign my data is equals to data 1, data 0, data 2, like this. These are different packets of data. I have 3 different packets of data. So what I am doing is only assign the data if all the data packets are received. So I am creating a event called receive data. So the receive data is event that will be triggered only if my last data is arrived. Once the last data is arrived, then this event is triggered. So when this event is triggered, then assign all the individual data packets into my main data. Right? This is my main data. Inside my main data, I am assigning all the individual data packets that I have received so far. Right? So this is the purpose of named event control. You can control the event also. I am not using begin and end here because this is a single statement. Right? If you have multiple statements, you can use begin and end also. Now let's see what is event or control. Till now we have seen only single events, whether positive edge of clock or negative edge of clock or user defined event like always at the rate receive data. Only single events, right? Let's say if you have multiple events, in that case you can use event or control like this. Let's say you have multiple events like let's take an example of a latch, an asynchronous latch. The input of latch is D and the output of latch is Q. It has two different asynchronous inputs. One is clock and the other one is reset. Okay. So first I am defining always at the rate. The latch operation should perform both using clock as well as reset, right? When the reset becomes 1, then my Q should be 0. When the clock is turned on, then my D should go into Q. So both the things should control my next statements, whatever that I'm going to write inside the always block. So always at the rate, first one is reset, or I can use or raising. I should write properly. This is the syntax. You can use or reset or the clock, or even if there is a change in data also the Q should change, right? So or D. So any one of these three things will happen, the following steps will execute. The following steps will be like this: begin if my reset is equals to 1. If the reset is equals to logic 1, then what should happen? My Q should become 0, right? Else, if my reset is 0, then it should check for clock. If my clock is, else if my clock is high, so if my clock is high means then I want Q should be D, right? And then I'm ending this always block. I'm not using begin and end for if. because it is a single line. Here also it is a single line, so I am not using begin and end. So I am directly using begin and end for the always block. So what is happening here? First it will check for the reset signal. If the reset is 1, immediately put q is equals to 0. If my reset is 0, then go to this statement. Else, if my clock is again 1, then put q is equals to d. Okay. This is a latch that we have created a latch by using this always at the rate reset clock or d by controlling these statements, right? These values. So you can either use or you can simply write like this. You can write comma as well. The operation of both are same. So we'll call this as a sensitivity list. Sensitivity list. So whatever the list of variables that are available here, based on this their sensitivity, whether they are changing or not, the event will be triggered. That is why it is called sensitivity list. Okay. Now let's say if your design is very big, let's say it has lot of sensitivity parameters, like you have many variables a, b, c, d, e, f, g, so many variables. To define all these things inside the always block is not a feasible way. So in that case, what you can do, you can use at the rate hash trick. So what does the hash trick means? Whatever the inputs that are going to be inside your always block, they will become automatically the sensitivity list. Either you can specify all the inputs in the sensitivity list, or you can directly use hash trick. The hash trick will take care that all the inputs that are inside the always block. Okay, let's take an example. What I meant to say is, if you have a lot of variables that are changing inside your event like this, let's take my always block. I'm not defining what are the variables right now. We'll see what will be the sensitivity list. Begin my output 1 is equals to, I'm using a conditional operator like this. A is equals to b plus c or d plus e. So what does this do? If a is equals to 1, then execute this. If a is equal to 0, then execute this. Similarly, my output 2 is equals to a, b, c, d, e, f, b into c, d into c, c into e. So what does this do? It will check for f is equals to 1 or not, then it will execute. Let's take different variables b1, c1, d1, e1, right? So in this case, the sensitivity list should be all these things: A, B, C, D, E, and then F, B1, C1, D1, E1. All these things should be sensitivity list, because whenever there is a change in any one of these values, this block of code should execute, right? So defining all these things is a very tedious job. In that case, you can directly write always at the rate hash trick. So what does it do? It will consider all these things that are present in the right hand side as the sensitivity list and put it inside the sensitivity list. Whenever there is a change in the right hand side, it will execute the following steps. Okay, that is the purpose of always at the rate hash trick. You can use always at the rate hash trick like this, or directly you can write always hash trick. Both are same. Okay. Now finally we will see what is level sensitive timing control. Till now we have seen the edge based, right? Whether positive edge or negative edge. You can do the level sensitive also, whether logic high, that is logic 1, or logic low, that is logic 0. This is level, whether logic high level or logic low level. Level based also you can control. So let's take an example. In the level based, we will use a keyword called wait. So how to write the level sensitive timing control? We can write always. Okay, this is always wait if my control. This is my control signal. If my control is enabled, then after 25 nanoseconds, my count is equals to count plus 1. So what does this statement will do? Whenever the control signal is 1, then the count will be count plus 1 for 25 nanoseconds. So after every 25 nanoseconds, my count will get incremented by count is equals to count plus 1 if my control signal is 1, right? In this entire level, when my control signal is 1, at every 25 nanoseconds, my count will get incremented by 1. At t is equals to 0, if my control signal is like this, immediately at t is equals to 0, I turn down to 1. So at t is equals to 0, my count will be, let's say I'm initializing my count is equals to 0 in the beginning. So initially it is 0. At 25 nanoseconds, it will be 1. At 50 nanoseconds, it will be 2. At 75 nanoseconds, it will be 3. But if I turn down this count control signal, this is my control signal. If I turned off this control signal to 0, up to 100 nanoseconds, it will be executed 1, 2, 3, 4. After 100 nanoseconds, this statement won't execute, right? It will be 4, 4, 4 like this only because the control is 0. So this statement won't execute. So that is how you can control the flow using level sensitive also. So till now we have learned many things like what is an initial block, what is an always block, and how to do the procedural assignments using blocking and non-blocking, and how to do the event controlling or latch based controlling, timing controllings and all. Now we will see the examples like how to use the blocking and non-blocking statements, and how to use a clock divider, how to design a clock divider using different techniques. And in gate level modeling, we failed to create a synthesizable delay, right? By giving this, we tried to create a 2 seconds delay, but it was not happening in the gate level modeling because the statement is not synthesizable. But now we have seen the theory of how to use the delays and how to use the always and initial block. Now we can create our 2 second delay circuit, and I will explain by dumping the code inside the jetboard, and I will show you we can create the amount of delay we want. So particularly I will explain three different examples in this session. First, an example to define what is blocking and non-blocking statements, and in the second example, I will try to design a clock divider. If I give a 100 megahertz clock, let's say its frequency is 100 megahertz. If I want to create a 50 megahertz or 25 megahertz clock from this 100 megahertz, we can create. Even you can create a 1 second clock also by using clock division circuits. I will explain in this example. Based on that 1 second or 2 second, we will design a delay circuit and we will perform AND operation same as in the gate level model, but this time it will be synthesizable. So let's begin the live coding session. In the live coding session, I'll explain these topics. Okay. Hi everyone, welcome to the live coding session on behavioral modeling. In this session, I'm going to discuss three different examples. The first example will discuss the difference between blocking and non-blocking assignments. In the second example, I will tell you different ways that you can use the clock to get the clock divider. And in third example, I will create a 2 second delay that we are failed to design in data flow modeling, where we have used the non-synthesizable delay like this, right? But in this case, I will generate a synthesizable delay by using the system clock that is there inside the jetboard. From that system clock, I will try to get a 2 seconds of delay, and I will use an AND operation to perform every 2 seconds. Then I will show the output in the jetboard by using LEDs. So let's begin the examples. So let's create a project. Naming the project blocking versus non-blocking. We have already seen all these steps, right? So I'm doing very quickly. Selecting the jetboard, finish. We'll take the same example that we have seen in the theory. Okay. So I'm taking all the different outputs that I took: A, X, Y, Z, comma register A, register B, defining them as output registers X, Y, Z. Register A and B, I am defining a 8-bit vectors. and I'm taking one integer count. Okay, so let's assign x is equals to 1, y is equals to 0, z is equals to 1, and register A, which is a 7-bit data, 8-bit data, I'm assigning to 8-bit hexa 0. Similarly, register B equals to 8-bit hexa. Okay, now I am giving regular delay of 15 nanoseconds for register A. This is bit select because I am only assigning to a single bit of a vector, and I am assigning it to 1-bit binary 1. Similarly, I am giving a regular delay of 10 units for register B. This is part select. I am selecting part of the vector from 4 down to 2 and assigning 3 bits 0, 1, 0. And then I am incrementing the count. Count is equals to count plus 1. There is some error. So see, I am trying to do the procedural assignments without any initial and always blocks. So it is giving an error. So now I need to create initial. Since there are multiple statements, I have to use sequential blocks like begin and end, begin and end, right? Now there is no error except this. What is the error? X near double quotation. 3-tick binary, right? Now I'm saving the design and running a simulation. Since we haven't initialized any value to count, it went to don't cares. So let's initialize count is equals to 0. Okay, and run the simulation. Now let's see the output. Initially, my x, y, z are 1, 0, 1 that I have defined, and my count is equals to 0, right? After 15 nanoseconds, my register A of the second bit will become 1, right? So if I turn on radix binary, then you can see the second bit becomes 1 after 15 nanoseconds. Similarly, register B will get 0, 1, 0 data in 4 down to 2 at 15 plus 10, 25 nanoseconds, right? So we'll see whether it is true or not. See, at 25 nanoseconds, the register B data is changing to 0, 1, 0, right? And after executing these two statements, by count increment will get executed. So after 25 nanoseconds, my count is also incremented from 0 to 1. Okay, this we have already seen in theory. So in practical, we have proved that blocking statements will execute sequentially, right? Let's comment these three statements and use non-blocking statements instead of blocking statements. So I am commenting these three statements. So for multi-line comment, you can use backslash followed by hashtag like this. So this I am naming it as a case 1, where my outputs are, this is executing at time 15, this is executing at time 25, and this is also executing at time 25, right? So now let's see what happens if you give non-blocking statements, non-blocking assignments instead of blocking assignments, right? So same 15. So in the theory, I have thought non-blocking assignment using intra assignment delay, right? So I'm doing the same thing, register A, and then this is non-blocking assignment, then 15 time units delay, sending it to one tick binary 1. Similarly, register B, go down to 2, non-blocking, after 10 nanoseconds, assign it to 3-bit binary 010, and my count is equals to non-blocking equals to count plus 1. Now let's see the output. I'm relaunching the simulation. Now we'll start from 0. At time 0, x and y and z are readily available 101. And see, the count is also becoming 1 at time 0 itself. Since it is a non-blocking statement, these two statements are not blocking the count statement. At time 0, all of these 5 lines as well as this line is executing at time 0 itself, right? That's why my count becomes 1 at time 0. As in the case of blocking statements, the count becomes 1 at time 25. But in non-blocking statements, it became 1 at time t is equals to 0. Now let's see what happens for register A and register B. The register A will get at time 15 and my register B will get the data at time 10, right? At time 10 nanoseconds, my register B is getting 010 data, and at time 15, my register A is getting 1 data at second bit. So this is also true. So let's name this as case 2. Case 2. This we have seen in theory, right? So here the register A is executing at time 15 nanoseconds and my register B is executing at time 10 nanoseconds and my count is executing at time 0. Now let's define two more cases where the case 3 is I am defining intra-assignment delay for blocking statements. Okay, so I am copying this. I am using the blocking statements, but right now I am not using regular assignment delay. I am using intra-assignment delay. Now let's see what happened. I am relaunching the simulation. We are focusing on register A and register B and count, right? Let's directly go to them. The register A is changing at 15 nanoseconds and register B is changing at 25 and count is also changing at 25. So there is no change. Even if you give regular assignment delay like case 1 or intra assignment delay like case 3, in the case of blocking assignments, they are all executing at 15, 25 and 25 nanoseconds, right? Now let's define the final case, case 4, and then we'll conclude our hypothesis, what we learned from this. So I'm defining case 4. Let's copy the non-blocking assignment statements. And now I will give regular assignment delays. Save it, relaunch the simulation. Now see what is happening. See, at time 15 nanoseconds, the register A is changing. But in case of non-blocking statements, at time 10 nanoseconds, the register B should change. But here at time 25 nanoseconds, the register B is changing. Similarly, at time 25 nanoseconds, the count is incrementing. So we'll write here at time 15 nanoseconds A is changing, but at time 25 nanoseconds, the B is changing. At time 25 nanoseconds, the count is incrementing. So what is happening here? Even though if you are using non-blocking statements, if your delay assignment is different, then the amount of time it will take to execute those statements will be different. In the case of case 2, I am using inter-assignment delay. So what does this mean? First of all, it will calculate this expression and then it will schedule the execution of this statement at 15 nanoseconds. Similarly, it will calculate the right hand side part and then it will schedule the execution of this line of code at 10 nanoseconds. That's why it is executing at 10 nanoseconds and this is executing at 15 nanoseconds, as well as this is executing at 0 nanoseconds, because we are not scheduling at any time. So by default, it will execute at 0 nanoseconds. But in this case, we are giving regular assignment delay. Even if we are using blocking statements, it will first wait for 15 nanoseconds and then it will do this expression. Similarly, after 15 nanoseconds, it will again add the 10 nanoseconds to the 15 nanoseconds. At 25 nanoseconds, it will execute this step. Similarly, at 25 nanoseconds, the count is also getting incremented. So this is the summary you need to understand from this example, not just because of blocking or non-blocking assignment, but because of the method that you define the delays will also control the flow of your data, right? So with this, I am concluding the example of blocking and non-blocking. Now let's create a new example to create clock divider circuits.